Good day and welcome to our class on the Cauchy sequence. Today, we want to prove that a sequence is Cauchy, and we also prove that another sequence is not Cauchy. We start from the first one. Prove that the sequence minus 1 raised to power n over n squared is Cauchy. We want to prove that sequence is Cauchy. Minus 1 raised to power n over n squared. You want to prove that it is Cauchy. Again, we remember that the first thing we need to do is to recall definition. For every epsilon greater than 0, there exists a p belonging to the set of natural numbers such that a sub m minus a sub n is less than epsilon for all mn greater than p. If that is the case, we then need to identify p. We need to identify p. But for us to identify p, we will make some assumption here. Let m be greater than n. And if m is greater than n, it implies that 1 over m will be less than 1 over n. Therefore, let's try to identify our p. A sub m minus a sub n will be equals to minus 1 raised to power m over m squared minus 1 raised to power n over n squared. And this gives us minus 1 raised to power m over m squared plus open bracket minus 1 raised to power n over n squared. And we can use triangle inequality on that. And this will be less than or equal to minus 1 raised to power n over m squared plus minus 1 raised to power n over n squared. And so, a sub m minus a sub n will be less than 1 over m squared plus 1 over n squared. Will be less than 1 over n squared plus 1 over n squared. And since we want both of these to be less than epsilon, let 1 over m squared be less than epsilon over 2. That implies that our m will be greater than the square root of 2 over epsilon. And the same thing happens for n, will be greater than the square root of 2 over epsilon. And since m and n is greater than p, it further implies that our p is greater than 2 over epsilon. Having identified p, we can now go ahead to prove. let epsilon be greater than 0 and p be such that p is greater than the square root of 2 over epsilon. A sub n minus A sub n will be equal to, as we have there, minus 1 raised to power m over m squared minus 1 raised to power n over n squared, and this is less than or equal to minus 1 raised to power m over m squared plus minus 1 raised to power n over n squared, and this is less than 1 over m squared plus 1 over n squared, which will be less than 1 over p squared plus 1 over p squared, since m and n is greater than p. Therefore, the absolute value of A sub n minus A sub n will be less than, as we said there, 1 over p squared plus 1 over p squared, but our p is greater than 2 over epsilon, the square root of 2 over epsilon. Therefore, p squared will be greater than 2 over epsilon, and so A sub m minus A sub n is less than 1 over 2 over epsilon plus 1 over 2 over epsilon, and that is less than epsilon over 2 plus epsilon over 2, and that is less than epsilon. Therefore, the sequence minus 1 raised to power n over n squared is a Cauchy sequence. And that is what we have been able to prove. We'll prove the second one, that is not Cauchy, to show that the sequence n squared over n plus 1 is not Cauchy. Show that the sequence n squared over n plus 1 is not Cauchy. To prove this sequence, we will recall some theorems. The first theorem we are going to recall is that a sequence is Cauchy if it is convergent. A sequence is Cauchy if it is convergent. So to show that this sequence is not Cauchy means that we are going to show that the sequence is not convergent. This implies showing that the sequence n squared over n plus 1 is not convergent. And if it is not convergent, it means that the limit of the sequence does not exist. Let's go ahead and show that the limit as n tends to infinity of n squared over n plus 1 truly does not exist. This is equal to the limit as n tends to infinity of n squared over n squared of n over n squared plus 1 over n squared. And that is equal to the limit as n tends to infinity of 1 over 1 over n plus 1 over n squared. And that is equal to 1 over 1 over infinity plus 1 over infinity. That's equal to 1 over 0 plus 0. And that is equal to 1 over 0, which is equal to infinity. Therefore, limit of the sequence doesn't exist, and that implies that the sequence is not convergent. And since the sequence is not convergent, it means that the sequence is not Cauchy. If you have benefited anything, or if you think this class is meaningful to your real analysis lessons, give it a thumbs up and share with your friends and colleagues.